Maybe I need to recalibrate. There we go. All right. So we're really looking at the conditions for being able to use the mean value theorem, which are what? Do you remember? So in order for the mean value theorem to apply, stuff has to be true. So if we go back to the theorem, it's this if part. So if a function is continuous and differentiable, so it has to be both. So really we need to check if that's true. Yep. And thinking of this like a multiple choice, so we know we have like a minute or two, right? How could you quickly decide that?
Well, how would you know?
Yeah, well, so thinking back to where, I think that was unit 1, well, continuity was, and then differentiable was unit 2. So for it to be continuous, what had to be true?
Well, like,
Okay. So we'll probably have to go back and review that, or not, we do, I mean for all of us. This is how we defined it from unit 1, sorry. So the limit had to exist. Yeah, exist and is equal to, I need to put some kind of f of x in here, and is equal to f of a. So remember something like, if we had like, actually let's make it this kind. So in that case, the limit from both sides was the same, the limit from the left and right, but the f of a value was not the same as the limit. So that was a discontinuity. So that was a removable discontinuity, where we could solve to plug that hole by finding the value of y. Okay, that was removable, which kind of tells you, well, hey, there must be non-removable. So that was things like, well, you tell me, do you remember?
it was like, well, removable is like the circle ones like that don't have.
Yeah, like I just drew,
Yeah, like you just
where we could plug it.
And then, what do you mean by like the other ones? Like,
Well, so non-removable would be one that doesn't just have a point to fill in. There's one word I could say, but it might give it too much away. But I'll say it. So it's infinite discontinuity.
oh, so if it's like, if it just keeps going?
Yeah, like maybe it's something like this.
Oh, yeah.
What
so
do we
like
call the dotted line? Vertical asymptote. Yeah.
Sorry.
So like an asymptote where the function is undefined, right?
Yeah.
Or it's just completely not part of the domain there. Okay.
Oh, okay, now I see.
And then differentiable, we're looking for things like this is differentiable on its domain, this one I just drew. But remember, we're looking, like we keep seeing in these pictures, like if we had something like that, it's not differentiable there. Well, that's going to be hard to tell just by looking. But this isn't, right? We can figure this part out. This one would be discontinuous if the denominator is 0. So does sine of x ever become 0 on that interval?
Yes.
It does, right? Because where does sine become 0?
When x equals 0.
Yep. And? Yeah, like thinking of the sine function, where is it 0? So this is an ugly unit circle, but it's sine is 0 there. Where else? Sine of 0 is 0. Sine of pi.
Oh.
Sine of pi is
Okay,
0.
yeah, we're going back to this.
Okay. Is pi on the interval negative 5 to 5? Yeah, because it would be 3.14, right? Or negative.
Yeah.
Okay. Anyway, so this one is out. Because it's going to have asymptotes there.
Yeah.
In fact, we could graph it. I mean, just so we know. Not on your test, but just so we know. Oh, I forgot to divide. Hold on. 1 divided by sine of x. Okay. So definitely discontinuous,
Yeah.
right? Okay. How about this one? On the interval negative 5 to 5, does this ever have a 0 denominator?
It does?
Yeah. Yeah, because if I plug 1, 1 minus 1 is 0, right?
Oh, okay. And then, okay, I see. And that's in the interval, so you can plug it in.
Yep. It's going to look something kind of like that, I think. So it's out. Okay? This one is x squared over x squared minus 36. Does that ever equal 0? The denominator, I mean. No, because if we set this equal to 0, we'll get plus or minus 6, right? And that isn't in our interval. Okay, and then how about this one? X squared minus 4 equals 0. X equals plus or minus 2. That is in our interval, right?
Oh, yeah.
So that one can have a vertical asymptote. So this one is our answer. So the sorry.
So that you can use the mean diagram on that.
Yes, because it doesn't have a discontinuity. At least not on our interval.
Yeah.
So really what this problem boils down to, because you could look at it and be like, man, I have to take the derivative of all those, and that would be a lot, right? So check discontinuities first, and for that I would check 0 denominators first. Can the denominator be 0? If yes, kick it out. Yeah.
You only have like a minute on these questions.
Yeah, I think we read it was like 2. It's short. Yeah. Good? How'd the homework go? Okay.
You made us do all the eating.
On 5-2, yeah.
We just do five for 6.
Number 6?
Yeah, we could just go over it.
Just what?
We could just go over it.
Just that one?
Yeah, just that.
Okay, so finding the critical points. So remember the critical points are at f prime, where f prime equals 0 or f prime doesn't exist. So first is to take the derivative, so h prime. So I'm going to do a u substitution, and then for this, say h equals u to the 1/3. So h prime is dh du times du dx, just kind of reviewing chain rule. So for this one, 1/3.
Why would you have to use chain?
Because we have this function is inside of a function. Okay. So I always do this, even if it's maybe just in my head, but a lot of times I'll write it. Yeah, and like if this had something even inside of it, then I would call that b, and I just think through it this way, like take the derivative of the main thing, the way I wrote it as u to the 1/3. So we're just taking the derivative of it regarding u, and then u to x. Make sense?
Yeah.
So 1 over 3, bring the 1/3 down, and then subtract 3/3.
Subtract 3/3 from 1/3.
Yeah, so we have to subtract 1, which is 3/3. So 1.
So then it'd be negative 2/3.
So that's smaller. 1/3 minus 1 is negative 2/3. Remember, the negative is going to put it down here. So this is going to be u down here to the 2/3. Right now, I'll just write it as u. Okay, and then times du dx, which is just 1. Right? But if this had been anything else, this would not be a 1. Like if it had been 2x or x squared or something, then that would not be there. Okay, now we can plug the u back in, and probably at this point turn the exponent back into a radical. So which 2, which goes on the x minus 2, and which is our index?
So the index is 3 and 4.
Yeah, good. All right, so there's our. Yep. We're looking for where it equals 0 or where it doesn't exist. So if x is 2, and this becomes 0, and we're squaring 0 and taking the cube root of 0, and the whole thing is 0. So it doesn't exist there, right?
Yeah.
So there's one possible local or global extreme. And then how about, will this ever equal 0? So if we ignore x being 0, can the whole thing be 0? Is the next question.
So you would just set it equal to 0, right? Like to see if
Yeah. Which then when we solve, so if we think about setting this equal to 0, we would multiply by the denominator. But then it says 1 equals 0, which doesn't really make sense, right?
Yeah.
And if we just think through it, this is an issue, so we're not going to consider x being 0. But if x was 1, this whole thing always will be positive, right? Because it's squared. Cube root of 1 would be 1.
So then it would never.
And then that's a third, right? And then no matter what's in here, if we think of x being big, like let's say 100, cube root of some big positive number, 1 over 3 times that is still defined. It's not 0. And then if we make it negative, it always becomes positive, so it's never going to be 0, right? Okay. Let's just write it this way. H prime of x is not equal, there's no places where it's equal. Does that kind of make sense?
Yeah.
So there's one critical point at x equals 0. And let's cube root of x minus 2. Let's graph it just to see how it looks. I'm going to write it though as x minus 2 to the 1/3, which is the same as cube root. Okay. So remember that we're not looking at where does this equal 0, but it slopes. So we can see that this is always increasing, right? Except for right here, where it doesn't exist, the slope would be infinite because it's a vertical line.
Oh, okay, that makes
So that's where that's sorry, excuse me. Yeah. That looks like it should be at, well, I don't know what my scale is for this. Let's see if it's on standard, yeah. It looks like it should be not at 0, but at like 1 point something. You see what I'm saying?
Yeah.
Wonder if we can get zoomed in on that. I should be using our other calculator. Honestly, it's just better. Yeah, there's that vertical looking slope. Yeah, I didn't mean to say 0, I meant to say at 2. That's what we talked about.
Yeah.
When x is 2, it's 0. Okay. That's better.
Oh, okay, I see that, yeah.
When x is 2, it makes that whole thing 0, not at 0. Yeah, I said it wrong. Yeah. Anyway, that's kind of how you work through that. Does that help?
Yeah.
Okay. Any others?
No.
So we're in this section, we're looking at figuring out where a function is increasing or decreasing, but without having to graph it. So this goes back like to algebra 2. Remember doing intervals of increase and decrease?
Oh, yeah.
We always had to see a graph, or most of the time. So, sorry, we're going to do some more justifying in this. But this time we're going to be able to do it based on derivatives instead of just graphing and looking at. Yep. Which is, I think, kind of cool if you think back to how that was, and it was kind of a pain. This is nicer, I think. Yeah. And the notes on this are kind of long, so we'll try to get through it quickly. So we've seen a graph like this before, but it says find the critical points of the graph. Where would those be?
Would be like at 3, 5, and then that would be it, right? Because 6, that's a cusp, so
Well, but it's a critical point because the derivative wouldn't exist there, right? So f prime
and
equals
if it doesn't
0.
exist, then that's
Yeah.
Okay, so then it would be the 6.
Good. So the derivative doesn't exist. Still is a critical point. And what would you call that if we were just naming? It's still a local max, right? Even though.
It could be local max.
So, first find the critical points, like we just did on the problem you asked about, where you would have to find the derivative, set it equal to 0, and figure out where it's not existent. So that will be part of our process. And we're looking for what happens when the graph or the slope is positive. That's increasing, right?
Yeah.
And I mean, this is kind of just review from algebra 2. So, but it's important. So positive slope is increasing, negative slope is decreasing. So what we'll do, and after this one, and when you're working on your own, you'll have to set up your own tables. But basically, we're going to write in our critical points and then leave space between them to figure out what's going on. Yeah. So, like our first one is at 3, so x equals 3. What's the sign of f prime there? It's kind of a weird question.
What do you mean like the sign?
Yeah, so the sign of the slope.
Oh, it would be positive, right?
At 3.
Yeah.
So that would be like what our tangent line looks like.
So that would be,
So what's the slope of that?
oh, 0.
0, yeah. Okay, and then our next one is at, is it 5? I can't really read it.
Yeah.
1, 2, yeah, 5. Okay, and the slope there is also 0. Okay, and then 6, what's the slope at that one?
0.
Or the sign of the
doesn't
derivative,
exist.
yeah. Okay. Then, in between here, we're going to figure out the sign of a value. So, if we go from, so our x values are going to be negative infinity to 3 on an open interval. What's the sign of f prime?
It would be negative, right?
The slope is positive, right? So f
Oh,
prime
yeah.
would be the slope of that section. Okay? And then 3 to 5, again, open interval. So between those two, what'd you say?
Negative.
Yep. And then 5 to 6.
Positive.
Good. And then 6 to infinity is negative again. Okay, so then if the question asks, well, where is it increasing or decreasing, we could just go in here and read. So increase, decrease, etc., right? So think ahead to not having the graph, but just having a function rule. We can create, we don't have to have this graph to create this table, do we? No. So that's how we'll do these. That way we don't have to have the graph. So first find the critical points. What do we have to do to find those? Yeah. So let's find f prime negative 2x minus 4. And that is a line, right? So it always exists. There's no does not exist part. So that's, we're not going to get any critical points from it does not exist. But we could get one from where it equals 0. So set it equal to 0, and we'll get x equals negative 2. So x equals negative 2 is a critical point. This is really a statement, nothing to do, but it's important that in between those, in this case, on either side of, right, it has to be positive or negative. So let's divide this up into 3 sections because we know we have one at negative 2. Our slope there is 0, since that's a critical point. That does exist. Or I mean the derivative does. So from the left and from the right, or to the right rather. Okay, so how do we find the sign of f prime left of our critical point?
Well, since it's like negative infinity, you can think of like negatively it's big. Does that make sense? Like if you put it into the function, and then you can see it's like positive or negative, and that's what you can get.
Yeah, just pick a value.
Yeah, just like pick a value.
In that interval. And we don't care about the actual value.
You just care.
Yeah. Yep. So we'll get what? What would you pick?
Like 5 or something.
Okay. So it's going to be positive, right? Up to, if we did negative 2 is our critical point, so this is always going to be positive. Okay? And then over here, what would you pick in that interval?
0.
Awesome. And that's going to be negative.
And then to justify, you just be like it's increasing because the sign is positive, or is it? Or would you be like it's greater than, or like to justify, you would be like it's increasing because the function is greater than or greater than.
Okay.
0.
Well,
Does that make sense?
yes, it does. Yes, we'll say that, except for we have to say f prime, not f. Yeah. So we'll say it this way. F, the original function, is increasing on the interval negative infinity to negative 2 because f prime of x is greater than 0. That's what you're saying.
Yeah, that's what I was like.
Yeah. And so the other one is decreasing because it's less than 0. And if we look back at the original function, what kind is it?
It's just a line. Or what do you mean?
The original f.
It's a polynomial.
Oh, what?
Polynomial.
Yeah, but specifically a parabola,
Oh, yeah.
opening down, right? So it makes sense that there's one interval of increase and one of decrease. We just had to find that maximum, the critical point where the maximum takes place. So if we overlapped this with like algebra 2 stuff, if we did like negative b over 2a to find that vertex, we would see that that is this right here. It's like negative 2. All right, cubic one. So what do cubic functions look like?
Well, they just kind of like.
Yeah. Well, just one.
Yeah.
Usually just like that, of various heights of the bumps.
Yeah.
Like sometimes it could just be like that. So we don't know which one it might be. Like this would, how many critical points would there be there? None, yeah. So it could be that. Or we could be looking at a case here where it has 2. So, same process, right? So, to do the derivative, tell me about this derivative, the graph, or the nature of this derivative.
Like the what it looked like. It was
Yeah.
just like
Parabola, opening up. So it exists everywhere, right? So that's not going to be an issue. So this is where we'll check f prime equaling 0. How do you solve for zeros there?
Just active.
Yep. Do you do star method or guess and check or what?
Star method, or I kind of just look at it and see if it. Like,
Yeah. Like these kind of things.
Yeah, like easy.
Yeah. Okay, so this time we have 2 critical points, so we'll need
6, right? Or
4. We'll need 5. 1, 2, 3. We need 5 sections because we need space on both sides of the critical points.
and then I would kind of just do the same.
Yep, same thing from there. Are we good on that?
Yeah.
This one, it's plugging in to a little bit more complicated function, so it's nice that you don't actually have to have the value.
Yeah. But can't you just put it like can't you just plug it into the factor form to find out? Would it just be easier?
Yeah, you could. It's like our first interval, negative infinity to negative 3. What would you pick? Why is it doing
Like negative 4 or something.
it? Okay. Huh?
Oh, negative 4. I just like something light.
Yeah, I don't know why it's there. I think it's fixed. Yeah, so negative 4, 5, 10, maybe negative 10. Good. But yeah, you could plug it in there. If you did negative 4, that would be negative, and negative, so it would be positive, right? Okay. All right, are you good on the rest of that? With the justification and everything? Okay. This one's kind of quick. So determine the intervals where f is decreasing and increasing and decreasing based on the graph of. This one's quick but super important. So let me say it that way. In fact, I'm going to put a star here.
Since this is a derivative.
Yeah.
So you just plug wherever it's like above the x-axis.
Good. Yeah.
And then it's decreasing.
So we're looking for where f prime is positive, f prime is negative. So this is a big deal in the AP world. So what intervals would you have for?
So from negative infinity to negative 3.
Yep. And
then from then read it.
Yeah. So the big deal there, I think it's good to get it, but the big deal is reading carefully. Huh? 'Cause
Yeah,
they could,
to make sure which graph you're looking.
yeah, they could burn you pretty easy. I feel like.
Yeah. And especially since like you're in that you're not gonna be stressed, but you probably are gonna be a little bit stressed. Yeah. You are gonna be stressed.
Yeah.
But like, you know,
and certainly working with like a pace and.
yeah, because you have to be on time.
Yeah.
So,
Okay, this one, back into application. So we already know this. If you want to know if it's increasing or decreasing, look at the sign of the rate of change. And what is changing in there?
what do you mean?
So this next phrase, the sign of the rate of change can tell you if the what variable is increasing or decreasing. Dependent, yeah. So that's the y variable. So on this first one, students per year is greater than 0. So we interpret this as the number of students is what?
Increasing.
Yeah. Okay.
The number, wait. The miles is decreasing. Wait.
Yep.
Yeah. The number of miles is decreasing.
All right, this one's different with
Since
that
it's
too.
squared,
Yeah.
that means that it's derivative, right? So then the rate of change is changing, right?
Yeah.
The rate of change is increasing.
No.
No?
You said increasing, right?
Yeah. Oh yeah, it's decreasing.
Yeah. So kind of a weird way to see it, but yes. And this is per month, right? The rate of the cases actually needs to say per month right there.
The rate of change in cases per month. That makes sense.
Okay. All right, last one. So big deal here again is to read carefully. So what is given?
So the derivative, right?
Yeah. So this, even though it doesn't look like a derivative function, it is, right? Okay. So show the number of flies is decreasing at 3. So the question is, do we use this function or do we need to take its derivative?
We use the function.
Yeah. So since it's a derivative, so use it to determine.
So you just plug in 3, right?
Yeah, so we'll just use R of 3. Seriously. I think that's probably going to work. Negative 5.4667. Okay, so what does that tell us? So the rate, or the number of fruit flies is decreasing. So this is something you could, if you wrote decreasing at a rate of negative, that's that double negative
Oh,
thing.
it's double negative.
And you could, yeah. So make sure you word it without that.
So how would you word it so you don't get confused?
Yeah, so the number of flies is decreasing. And it doesn't tell us to give the rate,
So then you
so you don't have to say. But we could just say because the rate is, and of course add a word, the rate of fruit flies is less than 0. Or technically this one would be better to just say because R of 3 is less than 0, that's how you should say that one. Because R is the rate. Yeah.